Hello everyone, and thank you for your interest in our paper. My name is David, and today I'm excited to talk about our work, Soundify, matching sound effects to video. This work was made possible with Anastasis, Chris, and Yining from Runway, and my advisor, Nick. The sounds of this video were automatically matched and mixed with Soundify, a system we developed to support video editors in editing sound. Now allow me to tell you more about Soundify. In this talk, I will first introduce our motivation. Next, I will present an overview of Soundify's system design. Then I will show a quick demo of Soundify in action. And finally, I will discuss future directions. Motivation. In the art of video editing, sound is really half the story. A skilled video editor overlays sounds such as effects and ambience over footage to add character to an object or immerse the viewer within a space. Sound breathes life into the visual world. However, through conversations with professional video editors, we found that this post-production process can be extremely challenging and time-consuming. More specifically, video editors identified three key bottlenecks: finding suitable sounds, precisely aligning sounds to video, and tuning parameters such as pan and gain frame by frame. In this paper, we ask, can we automatically match sounds, such as sound effects and ambient noises, to a video, including aligning and mixing parameters? Prior works have largely explored either learning audio-visual correspondence from large-scale data, such as look, listen, and learn, the sound of pixels, audio-visual event localization and unconstrained videos, and more. Or performing audio synthesis from scratch, such as WaveNet, Visual to Sound, Auto Foley, work done by the Google Magenta team, and more. In this work, we take a different but rather straightforward approach by leveraging labeled studio quality sound effects libraries and extending Clip, a neural network with impressive zero-shot image classification capabilities, into a coarse zero-shot detector. We are able to produce high-quality results without resource-intensive correspondence learning or audio generation. System overview. Classify. We match sound effects to a video by classifying sound emitters within. A sound emitter is simply an object or environment that produces sound and is defined based on Epidemic Sound, which is a database of over 90,000 high-quality sound effects. To reduce the number of distinct sound emitters to classify simultaneously, we first split the video into scenes using a boundary detection algorithm based on the absolute color histogram distances between neighboring frames. To construct a realistic soundscape, we then classify each scene for two types of sounds: effects, such as bicycle, camera, keyboard, or ambience, such as street, room, cafe. For a given scene, we run each frame through the clip image encoder and concatenate them into a representation for the entire scene. For each effects type label in the sound database, we run it through the clip text encoder. We then perform pairwise comparisons between the encoded scene and each encoded effects label with cosine similarities, and obtain the top 5 matching effects labels for the scene. The user may select one or more recommended effects, or by default the top matching effect is assigned. For ambient sounds type labels, we perform the same encoding and pairwise comparisons as the previous slide. However, ambience classification can be more error-prone due to the background often being visually out of focus or occluded. Thus, we additionally run both the predicted ambience and the previously user-selected effects through clip text encoders, and re-rank the predicted ambience based on their cosine similarities. For example, forest may be ranked higher than cafe if the user had previously selected waterfall. The user may select one recommended ambient, or by default, the top matching ambient is assigned. Sync. A sound emitter may appear on screen for only a subset of the scene. Therefore, we want to synchronize effects to when the sound emitter actually appears. We pinpoint such intervals by comparing the effects label with each frame of the scene and identifying consecutive matches above a threshold. There may be multiple intervals, such as when a sound emitter disappears and then reappears. Mix. Video editors adjust sound according to the state of the scene. For instance, as a bicycle paddles from one side to the other, we hear a shift in stereo panning. As an airplane glides up close, we experience a gain in sound intensity. Similarly, we mix and affects pan and gain parameters over time. To achieve this, we split an effects interval into around 1 second chunks, mix spatially aware sound bits for each chunk, and then we stitch the chunks together smoothly with crossfades. A spatially aware sound bit uses the first image frame of the chunk as the reference image. We run the reference image through GradCam on the radio activation of the last visual layer of the Resident 50 architecture to generate an activation map. This localizes the sound emitter, functioning close to a coarse object detector. We then compute the pan parameter by the x-axis of its center of mass and the gain parameter by its normalized area. Next, we retrieve the effect's corresponding wave audio file and remix its pan and gain parameters. For ambience, we assume a constant environment for each scene, thus we retrieve the corresponding wave audio file and simply use it across the entire scene. Finally, we merge all the audio tracks of effects and ambience of all scenes into an output video. Now, let's see a quick demo of Soundify. First, let's have a look at our input video. It has many scenes and has no sound. Now, let's add sound to it with Soundify. The video is first split into scenes. We see, for example, that Soundify has predicted a bicycle sound effect in scene 1. We can also add an ambient sound. Note that this is partially based on the selected effect. The similar goes for the other scenes, so on and so forth. Now let's generate the sounds. I've also printed out some intermediate visualizations and our pan and gain parameters across the video. Now let's have a look at the results. Or better yet, let's listen. I hope you enjoyed this quick walkthrough of Soundify. Future directions. Our next step is to evaluate our system through a user study with professionals and novices. Here's a screenshot of our current work-in-progress interface integrated into the SQL video editor. A quick introduction to SQL. SQL is a web-based professional video editor powered by machine learning, developed by Runway. SQL reinvents traditional video creation with a series of AI tools, which currently include an interactive video segmentation tool and a video and painting tool that speed up time-consuming and manual processes in video editing workflows. Next, there are also some failure cases for videos requiring very fine-grained audio synchronizations. For example, sounds such as individual footsteps can sound out of sync. Exploring more fine-grained synchronizations for such cases can help make the matches even more seamless. Finally, we'd also be interested in discussing with the community about the interactions between AI and designers. Some open questions may include: what role does the AI play in creative tasks? What are the differences between design tools for professionals and those for novices? How can we evaluate creative AI when the results are subjective? And when the AI is not 100% perfect, how good is good enough? In summary, our work explores how we can match sounds to a video by extending clip into a zero-shot detector and leveraging studio-quality sound effects libraries. To find out more, I invite you to visit our project page. Please reach out with any questions and have a good time at the NeurIPS ML for Creativity and Design Workshop.